Welcome back to another explainer. Look, if you're gearing up for a math exam or, maybe you just want to understand the exact mathematical laws governing the physical space around us, you are absolutely in the right place. Today, we're breaking down the absolute foundations of mensuration. Think of this explainer as your ultimate blueprint for mastering geometric math and spatial reasoning. We're going to make sense of literally every formula you need to succeed. Okay, let's dive right into this. We're going to start with a quick welcome to mensuration. Then we'll be mastering 2D shapes, stepping up into 3D solids, conquering compound shapes, and wrapping up with some absolute life-saving exam tips and mistakes to avoid. All right, kicking things off with Section 1. Welcome to mensuration, the true blueprint of geometry. Now, I know mensuration sounds like a highly complex, kind of intimidating word, but seriously, don't let it fool you. It's simply the branch of math that's completely dedicated to the measurement of geometric figures. We're talking about finding lengths, mapping perimeters, calculating area, and determining both surface area and volume. And honestly, whether you're studying for your GCSE, IGCSE, or IB MYP exams, mastering this math of physical space is absolutely essential. Let's move on and see how this all builds as we enter Section 2, Mastering 2D Shapes. We're transitioning from simple one-dimensional lines straight into two-dimensional spaces. Right off the bat, we have to contrast two foundational concepts, mainly because mixing them up is a massive, incredibly common mistake that students make all the time. Notice how perimeter is the total distance around a closed figure. It's a 1D measurement. Think of it like walking along a fence. Area, on the other hand, is the actual space enclosed by that shape. It's the grass inside the fence. That's a 2D measurement. So, golden rule, never ever confuse the distance around with the space inside. So most of these perimeter formulas are wonderfully straightforward, right? For squares, rectangles, triangles, and regular polygons, you're literally just adding up the outer boundaries. But slow down for a second and look at the bottom row, the circle. A circle's perimeter is called its circumference, and it's uniquely defined by pi. The formula is 2 times pi times the radius, which, if you think about it, is exactly the same thing as pi times the diameter. And this brilliantly illustrates how we calculate the space inside those shapes. Because area is two-dimensional, you're going to notice a really distinct pattern here. We're almost always multiplying two dimensions together. Whether that's squaring a side, multiplying length by breadth, or having the product of diagonals for a kite, it's all about multiplying dimensions to map out that internal space. Circles, of course, have their own special set of area rules. The total area of a full circle, that's just pi times the radius squared. But exams love to test you on pieces of a circle. When calculating arc length or sector area, notice that theta over 360 degrees fraction at the start of the formula. Theta is simply the angle at the center of the circle. This formula works perfectly because you are quite literally just taking a fraction out of the full 360-degree circle and multiplying it by your standard circumference or area formula. Super simple. Okay, you've mastered flat spaces. Now let's step up into Section 3, stepping into 3D solids, depth and volume. Time to add some serious depth to our geometry toolkit. So the crucial point here is really understanding the difference between the outside and the inside in a 3D world. Surface area is the total area covering the outside of a solid. It's effectively a 2D measure wrapping a 3D shape, kind of like wrapping paper on a box. Volume, though, is the actual amount of 3D space occupied by that solid. It's how much water the box could hold inside. Make sense? When we calculate volume, the formulas share these really beautiful mathematical relationships. A cube is side A cubed. A cuboid is length times breadth times height. A prism is just its base area times its height. And a cylinder actually follows the exact same logic, pi r squared, which is a circle's base area, times its height. But notice what happens with pyramids and cones. A pyramid's volume is exactly 1/3 of its corresponding prism. And a cone? Exactly 1/3 the volume of a cylinder with the same base and height. That 1/3 fraction is totally your secret weapon here. And finally, the sphere's volume is 4/3 pi r cubed. Surface area requires a little bit more focus. A cube is 6 faces of a squared. A cuboid adds up pairs of its varying sides. For a cylinder, the total surface area is 2 pi r times the radius plus height. But I really want to remind you of a super tricky part here, and that's the cone. The total surface area formula for a cone is pi r times L plus r. That L is the slant height of the cone, which you calculate using the Pythagorean theorem, the square root of radius squared plus height squared. Please do not just use the normal vertical height. They will try to trick you with that. Oh, and for our sphere, the surface area wraps neatly to 4 pi r squared. All right, let's move on to section 4. Conquering compound shapes, the puzzle pieces. Because, let's face it, the real world doesn't just consist of perfect, standalone spheres and cubes floating around, does it? When an exam gives you a complex shape, just think of it as a puzzle. And here is your 4-part strategy to solve it. Step 1. Divide the compound shape into familiar, simple shapes. Just chop that house shape into a rectangle and a triangle. Step 2. Calculate each area or volume separately using those standard formulas we just reviewed. Step 3. Add or subtract these values where required. Like if there's a hole drilled through a cylinder, calculate the cylinder volume and just subtract the volume of the hole. Easy. Step 4. Always include the correct final units. Honestly, even the most insanely complex mensuration problems can be effortlessly broken down using just these 4 steps. Now, what is truly mind-blowing here is the sheer scale of geometry when units change. Just look at that number, 1 million cubic centimeters. Believe it or not, that is the exact equivalent of just 1 single cubic meter. Crazy, right? This conversions table is basically your lifeline. While 1 meter is 100 centimeters in length, when we move to area, 1 square meter balloons to 10,000 square centimeters. And in volume, as we literally just saw, 1 cubic meter explodes to 1 million cubic centimeters. Also, definitely note that for capacity, 1,000 cubic centimeters equals exactly 1 liter. Listen, if you try calculating a problem without matching your units first, it is a guaranteed, non-negotiable path to the wrong answer. Don't do it. We are in the home stretch now. Welcome to Section 5, Exam Tips and Mistakes, Acing the Test. These next tips are your ultimate keys to securing top marks and avoiding the traps that catch out so many students. Let's rapid fire through the most common pitfalls. Please don't become a statistic by confusing your perimeter fence with your area grass, or by blindly plugging a diameter into a radius formula. Watch out for doing absolutely perfect math, but then forgetting your square or cubic units at the very end. You also want to make sure you never omit the curved surface area when calculating a shape's total surface area, or dive into the math without converting your units first. And finally, avoid using a cylinder or prism formula for cones and pyramids, simply because you forgot to multiply by that 1/3 fraction. It happens all the time. So, how do you methodically tackle every single geometry question to guarantee those points? First, draw and label your diagrams clearly. Give your brain a visual anchor. Second, physically write the correct formula down before substituting any numbers. It completely stops silly errors. Third, convert your units before calculating and keep them completely consistent. Fourth, always use the actual pi button on your calculator unless the question explicitly forces you to use 3.14. And lastly, never round off your numbers midway through a problem, only round your answer at the very final step. We've traveled all the way from one-dimensional lines to the complex volumes of three-dimensional space, and you now hold the exact blueprint needed to decipher it all. So I'm going to leave you with this question. Which geometric formula will you use today to start solving the real-world dimensions around you? Take these formulas, tackle those exams with absolute confidence, and I will see you in the next explainer.